So we looked at those properties of limits, which are very helpful, but remember to break up a limit either as a ratio, product, sum. The two individual pieces have to converge, and what do we do if that's not the case? Something we saw previously in Calc 1 with functions is also true for sequences, and that's what's called the sandwich theorem. And essentially you've got a sequence of bn's that's sandwiched or trapped between these an's below and these cn's above. And if the two things above and below squeeze down to one limit, then the thing trapped in between is forced to go there as well. Let's look at a couple of examples real quick. We did something very similar to this in Calc 1. So the limit out at infinity of sine n over n. We saw this before as a function, sine x over x. It's a similar argument. So first of all, the reason we can't just use the limit properties is if you tried to break this up as the limit of sine n over the limit of n, that's going to infinity, and that doesn't exist, right? Sine just goes up and down, up and down. It's not headed to a value. But if we think about this just intuitively first, we know that sine of n goes up and down and up and down, and it's being divided by larger and larger and larger values, so it should tend to 0, right? And so the argument is by sandwich theorem. Sine n has natural bounds, right? So we can argue that sine n is between 1 and negative 1, and then over n. And now we know how to take the limit of these outside sequences. We proved it, actually. So the limit as n goes to infinity of negative 1 over n is 0, which is also the limit as n goes to infinity of 1 over n. So this is trapped between these two, and these two outside are both headed to 0. So by sandwich theorem, which I'd like you to say when you make your argument, what theorem you're using there. By sandwich theorem, the limit as n goes to infinity of sine n over n equals 0. So this was an argument that you saw for functions back in Calc 1. It still holds for sequences as well. One thing that should make you think of sandwich theorem immediately is something with sine or cosine, because sine and cosine, remember, are trapped between negative 1 and 1. And their limits don't exist out at infinity themselves, so the limit properties are out. Now, another one I want to look at is very similar to this, but it's something you haven't seen before. And that's the limit as n goes to infinity of negative 1 to the n over n. When we get to series, we're actually going to see stuff like this quite a bit. And let me rewrite that a little bit lower there. But it's very similar to this if you think about it. Sine is trapped between negative 1 and 1, right? It meanders back and forth. This little term here, since we're talking about sequences now, right? N is a natural number, so that's being raised to the first power, second power, third power, fourth power. But what is that doing? Negative 1 to the first power is negative 1. Then squared is 1. Then cubed is negative 1. 1, negative 1, 1. So it's just flipping the sign back and forth. 1, negative 1, 1, negative 1. This thing travels between 1 and negative 1, 1 and negative 1. So it's very similar behavior, except for this just jumps between those two values. The reason you never saw this before as a function is if this exponent is real numbers instead of natural numbers, it's a very poorly behaved function, because in between with the real numbers, you're taking roots, right? When you start getting into decimals, you're doing roots. And there's lots of roots where you can't take the root of -1. So as a function, this thing would not be continuous, would not be differentiable, would not be integrable. So all the things we like to do with functions in calculus, we couldn't do. So that's why this is really the first time you're seeing anything like this -1 to the n. But you'd make exactly this same argument, right? Sometimes this is -1 to the n, and sometimes this is 1 to the n. Half the time it's that, half the time it's that. So it's trapped, right, between those two. Actually, not strictly in between, but it's okay that it's equal. And then we just make this same argument again. The limit as n goes to infinity of -1 over n equals 0, which is also the limit as n goes to infinity of 1 over n. So by sandwich theorem, the limit as n goes to infinity of -1 to the n over n equals 0. Trapped in between. Again, you couldn't use the limit properties, right? Because the limit of this doesn't exist. It's just going 1, -1, 1, -1. That's going to infinity. So now you've got something else to look for. So definitely sine and cosine should get you thinking, possibly sandwich theorem. Also, this little alternating sign flipper there, -1 to the n, should get you thinking about that. Now let's take a look at a graph of what's going on here, just so we can see visually what's happening with this sequence. So here what I've got, in Desmos, what I've done here is just graphed the sequence, -1 to the n over n for the first 200 terms. And you can see there how I'm doing that in Desmos. When you're first getting comfortable with sequences, I would actually recommend that you try that. So that first statement's just defining my terms. The second statement's making a list. It's going to make n go from 1 to 200, so it's a list of the first 200 integers. And then the third statement there is just defining the dots to plot. Now, what I've got below there is the functions 1 over x, so we can just see how that's laying. So half the time it's 1 over x, well really 1 over n because we're at the natural numbers. And the other half of the time it's -1 over n. So I've just graphed those functions for us so we can see that. Those are the two things we were using to sandwich. And it's not strictly in between there, but again, it doesn't matter. Being equal is fine as well. And we see both those functions as we go out to infinity are getting closer and closer to 0. And so that forces our original sequence there to get closer and closer to 0. Just to emphasize what I was saying about why you never looked at this as a function in Calc 1, there's the graph of the function -1 to the x over x. You'll notice there's nothing there. That's because Desmos is trying to plot those points, but infinitely many times it's trying to do it, it's getting does not exist, does not exist, does not exist. So there's, on any interval, there's infinitely many times this function here doesn't exist. So that's why you never saw this f of x here in Calc 1. But as a sequence, it does exist, right? If we're only looking at natural numbers, that thing is fine. It's got big gaps in it, but all sequences do. So this is something new we'll see quite a bit, this -1 to the n over n. And really the way to deal with it is sandwich theorem.